Okay, in this problem, there's a cheerleader shooting souvenir t-shirts out of an air cannon. I don't know if you've ever seen those before. They are pretty cool. I saw one recently. I was at a baseball game, and during the 7th inning, they were shooting things out of an air cannon. That's what I thought of when I wrote this problem up for you. This person would like to calculate a couple things. The maximum height that the t-shirt could go to in case they want to shoot it up into the cheap seats, and the range that it wants to go to, and how much time it spends in the air. So what we know, if this cheerleader holds it at a 70-degree angle and it launches at 40 meters per second, and I'll be honest, I doubt they actually go that fast. That would be dangerously fast. But if they did, we can calculate all this stuff. The first thing I need to do is I need to split that 40 meters per second into its x and y components. So what we have down here is it's a little bit of practice with our vectors. If it's shot at a 70-degree angle this way, at 40 meters per second, we need to split that up into how much of that velocity is in the x and how much of that velocity is in the y. So to find the velocity in the y, I used sine 70, because that was the angle, times 40 meters per second. That was the hypotenuse. Turns out that the velocity in the y direction is 37.6. Same thing for the x direction, except I used cosine. The velocity in x direction is only 13.7 meters per second. Now, when it comes time to use those formulas, I'm not allowed to mix up my x and y components in the same formula. I have to keep track of what happens in the x and what happens in the y. Okay, well, the first thing that we need to do in this problem is find the maximum height. And this is a good review of a thing I call the hidden givens. There are things that you're just expected to know about projectile motion, so they're not blatantly given in the problem. They're just sort of always true for projectile motion. So the one thing we know, in order to find the maximum height, what happens at the maximum height? We know that the velocity in the y direction at the top is always 0. Now, not the total velocity, just the velocity in the y direction. So the velocity in the y direction at the top is 0. I'm going to use that as part of my given. The other thing I know is that the initial velocity in the y direction was 37.6. Since we can assume that this happens on Earth, we also know that the acceleration in the y direction is gravity. I'm going to call that -10. As you know, technically it's 9.8, but I'm just going to round. And with this information, we should be able to find the maximum height. All right, so knowing what I know, I take a look at all my formulas, and I know the height is a displacement. So I'm going to have something that has an initial velocity, a final velocity, gravity, and a displacement. I'm going to use this formula. V final squared equals V initial squared plus 2AD. You may have found how much time it took to get to the top. You can do that too, and then plug that number into another formula and you'll get the exact same answer. So if you didn't use this formula, don't worry. We should get the exact same answer here in just a second. I know that the final velocity in the y direction, or at least at the top anyhow, is 0, so I'll plug that in right there. The initial velocity in the y direction was 37.6. That's going to get squared. Plus 2 times gravity. Gravity is -10, and I'll solve for that displacement in the y direction. So I put this into my calculator, and it turns out that the maximum height is 70.6 meters. So the maximum height, 70.6 meters. All right, we did part A. T total. This is another practice of the hidden givens. A bunch of different ways to solve it. Now that we know the height that it goes to, you could find out how much time it took to get there, and then how much time it took to fall. The time it takes to rise is equal to the time it takes to fall. Or, I'll show you another way to do it. We know that since it's shot in a parabola, the initial velocity in the y direction was 37.6. When it comes down, the downward velocity, the final velocity in the y direction, is -37.6. So we know an initial velocity and a final velocity for the entire trip, and gravity. So I'm going to use this formula. V final is equal to V initial plus acceleration times time. Now remember, never mix up your x and y components. I got to plug in all my y velocities and my y acceleration right here. So I know the initial velocity, or I'm sorry, the final velocity was 37.6. The initial velocity was 37.6. I'm missing a negative sign somewhere. Oh yeah, that one's supposed to be negative because it's in the down direction. Plus gravity, -10 times time. Here we go. Plug that into my calculator, and it turns out that the total time is pretty close to 7.5 seconds. I rounded a little bit. All right, so we got 2 parts done, 7.5 seconds. And this last one, the range, this is a good reminder that the velocity in the x direction is constant. If I'm trying to find the range, that's just a fancy way of saying the distance in the x direction. How far does it go before it gets back to the same height where it started? All right, well, I know how much time it spent in the air, and I know the velocity in the x direction, and since it doesn't change, I'm going to say that's an average velocity, or you can call it the velocity in the x direction, is the displacement in the x direction, that's the range, divided by time. I'm going to rearrange this and say that that displacement is the average velocity in the x times time, and it turns out that the range is 103 meters. All right, sorry that took so long, but there was a lot to do in this problem, and I wanted to remind you how to use all that stuff about the hidden givens. So hopefully projectile motion is making a little bit more sense. If not, try this on your own, and you might find out that if you use different formulas, you still get the same answer. All right, I'll see you in the next set of problems.